Topic today will be, say, roughly finite volume with focus on chapter 4, chapter 5 in the book by Versteg. Chapter 4 is quite easy. There's only the diffusion term in Navier-Stokes. No problem with those. But chapter 5 is a little bit bigger. And then also we cover the convective terms. They are a little bit of a problem. What we are aiming for is to understand now some of these additional input file into OpenFOAM. Something that is called FV files. And the first one there is called FV schemes. Now let's open this one with something, Notepad. No, let's not take Notepad. Let's try something else. Yeah, okay. We use Word. Here we have the FV schemes, and this one sort of informs OpenFOAM what discretization scheme will we choose for, and now it comes a whole bunch of names, and of course then we should understand what the heck they are talking about. This one, the FV scheme here, file here, has been stolen from the old Pitts-Daly case. I think the new one, the one you have been given, has a lot of entries here. But let's have at least have a look. First entry, DDT schemes, time derivative. It's a steady state problem. If you can recall Pitts-Daly, the backward facing step with the nozzle, it was with simple foam, which does not have a transient solution. It's only a steady state. So that makes sense. Gradient schemes. We have to find some way of describing nabla to the pressure gradient, but also the gradient of the velocity vector. They are normally not a big deal, so not too complex. Here, the div schemes, as they call it, that is sort of the problem. You'll have the combination here of an unknown, generic unknown phi, and the velocity. Here you are talking the convective terms, velocity times gradient of a function. And as you can see here, upwind, 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 upwind schemes. What do you know about upwind schemes? They are very, very, very bad. Linear schemes sounds better. Upwind, linear, and here also you get an idea what equations are going to be solved. So here all of a sudden you have phi and a k, phi and an epsilon and an r, nu tilde, nu effective, whatever that is. So a lot of turbulent quantities. Yes, if you can recall, the default Pitts-Daly case was with k epsilon. So here we have to also specify how should these equations be discretized. Laplacian schemes. There you are talking the diffusion terms, nabla square of something. So not so difficult. Still, some strange specification here, Gauss linear corrected, whatever that means. So this file is then something we will peek into. Okay, that was what we are aiming for to understand. And how to understand it? Well, we have the book by Versteeg, so we will start here. I also have some additional material I will show you later on. So we start here. Now the diffusion problem. The diffusion term in the Navier-Stokes, here written on the integral form. Remember, we are talking finite volume, not finite difference anymore. So you have it on an integral form. And what is very nice with volume integral of a divergence is, as you all know, divergence theorem, you can rewrite it as a surface integral over the fluxes, then over the surfaces of the inner quantity here that we are talking about, gamma being the generic diffusion coefficient. Just think of it as a viscosity if you like. And then you need a gradient of the unknown, generic unknown. You may or may not have a source term, which may or may not be constant. Still there, you see, you have to keep the volume integral, because it depends on how this source term, what it looks like. And further, then how to express these fluxes, these surface integrals, as actually not so difficult with either finite difference or finite volume or whatever. And remember, here in this equation, you don't have any additional velocity that sort of gives you a headache should we start thinking in terms of an upwind scheme or central space scheme. I mean, it's just a double derivative equal to 0 or equal to a source. So here you don't have a sort of possibility to go into the world of upstream schemes. So it's going to be a central difference scheme no matter what you do. And that will be second order, so it's actually not a big problem. Here, one-dimensional case. I mean, we have seen examples earlier with this equation. How to discretize it here in an integral form. And if you have the constant delta x, you will get the exact same scheme with finite difference. No difference there. So it's rather straightforward, actually. So here he wrote it sort of in the standard form, where you end up with an algebraic equation system given like this. I've shown you this earlier. You will have the in the x direction, if you are thinking in terms of a one-dimensional case, you always look at the center point P. And then you are talking about neighbors. And then we are talking east and west. And then if your cell is then something like this, in between the nodal points, sort of the nodal points are in the center of your volumes, then you are going to need a small eastern value here and a small western value on the cell faces. So when it reads it was up a sub small east, sub small west, you are talking these cell faces. And if you are in 2D, so you have a y direction as well, then you are talking north and south as well. And then a small north and a small south on the faces. And you can continue here with 3D, front and back if you like, no problem. Just to have that notation correctly. But you end up with an algebraic equation like this. Center point, the unknown in the center, multiplied with its coefficient AP, equals the sum of all the neighbors plus something constant, a source. So this is always what you will end up with. a discrete version of different partial differential equation. And here is now the question: what are these coefficients? And depending on the coefficients, will we get a solution? I mean, that's what we are interested in. And here, with a diffusion equation, yes, you will have some stability issues, not stability with respect to time. If you look at the equation here, it's you don't have a time derivative here, it's only a space derivative. But the question is, from the discrete version of the equation, can we still obtain a solution? I mean, that's what we are interested in, and how well is that solution. So we had some problems here with this equation, but normally not a big deal. You don't have much of issues here with the stability to obtain a solution. So as you see, I won't go through all these details here. The examples, they are quite straightforward, and the solutions, they will match quite nicely into the exact solutions for any example you care to investigate. I don't think he has much interesting examples here. No. Two-dimensional problems. So there you have the same stencil that I draw here. Center point P, north, south, east, west, and also then the value on the cell faces. So here, rectangular uniform mesh. The discretization will be exactly the same as if you had done it with finite difference. But with the finite volume formulation, you don't have to use a rectangular mesh, you can use any mesh. Well, not any mesh, but your volume doesn't have to look like that. It can look something like this in open form, not a problem. And then you have your center point P. And now it's a question, where is east, west, north, south? Well, now it's a total mess. You're talking unstructured meshes. So then you don't use this stencil anymore, but you look at, say, face for face. Each plane face around your volume has to be treated individually, but sort of in the same way as each of these four faces. The only demand, I think, in open form, when you construct a volume, you can have as many faces as you like, but they have to be convex. You are not allowed to make such a volume like this. This is not allowed. It's something to do with the fluxes going out here and actually collide. So he doesn't like that. That's not allowed. It must be only convex, not something concave like this. That's not allowed. But I think that's the only limitation actually in open form. So unstructured mesh, that's quite nice. So most of the examples in this book, of course, by structured mesh. So maybe not so realistic, but much more easy, of course. And here again you get the algebraic equation system. The center point equals sum of all the neighbors plus a constant. How to solve an algebraic equation system, that is something we are going to look into later on, because then you are talking the other file in open form, the other FV file, the one that was called FV solution. Then we decide how to solve a bunch of algebraic equations. So that will be at a later date. Here, three-dimensional, north, south, east, west, and top and bottom. So So it's just a name, and again you end up with the same thing. And summary, not a problem at all. So it's first when you introduce the convective term that you run into problems. So diffusion alone is not a big deal. It doesn't give you any problems, doesn't give you any errors, at least not any big ones. But now with the convection term as well, now we risk running into problems. We have spoken earlier also about diffusion. So physically, what does it mean, a diffusion mechanism? What does it do? Well, if you have a signal with a sort of discrete jump, any diffusion mechanism, he will tend to soften it down. He will smear out these sharp gradients. That's a diffusion mechanism for you. So this term, sort of stabilizing everything. Sort of you add viscosity into the problem, things get smoother, easier. If you are unfortunate and you introduce a negative viscosity, a negative gamma, then what's going to happen? Well, a negative diffusion, that's not so funny. It's not realistic. You don't find it in nature. But what's then going to happen is the opposite. So if you have a jump in any quantity, now he will increase the jump. And of course, the simulation then is going to explode. So a total diffusion coefficient here that is negative, very bad idea. Okay, let's see how now we handle this convection term. We do the same as we did with the diffusion term, with the convection term. It's written in the conservative form. You have a gradient in front. If you can recall from Sola, you had these terms, u du dx, v du dy. It's just a 2d in the x direction. We rewrote this one to be on the form d dx of u square plus d dy of uv. And to do that, we had to use the continuity equation. But yes, it was possible. And that's what has been done here. You have the gradient in front of whatever. And when you have that, then it's beautiful. Then you can use the divergence theorem and rewrite a volume integral into a surface integral. And the surface integral then covers the fluxes out of your cell faces. So here you have a flux of the sort of the argument that has been inside this divergence. Rho, unknown phi, and then a velocity vector. The diffusion term, as last time from chapter 4, you have a surface area. The source, well, that one you have to keep as a volume integral. This source term can be sort of anything. It doesn't have to be too complex. Think of it as gravity if you like. So that's just the gravity then multiplied with the volume. Piece of cake. Not a problem. The question is how to handle this first term now. These fluxes. And that is actually a big issue. So we have had some exercises with this already. And what we did then in exercise 2 in Sola, actually the original was programmed like this. And we went back to this form so that you have a velocity in front of a derivative. And then we reprogrammed it to a first order upwind scheme, depending on the sign of the velocity in front, positive or negative. So that was our first order upwind scheme, which we should have a conclusion is terrible. It's way too diffusive. You add a lot of viscosity into the problem. So you have sort of the same philosophy here initially in this chapter. He starts with a central differencing scheme, meaning to find these fluxes, you use a linear interpolation, which will then end up as a central differencing scheme. And running an example here, I think he has the same example as we looked at from the other book by Verziger. We have an analytical expression, analytical solution to this 1D diffusion problem, no, convection diffusion problem. And it turned out, as it should, that you get a very nice solution if you don't overdo it here. You need to have a cell Reynolds number smaller than 2, or else you start getting very crazy results like this. Very waggling solution from the central space scheme, central discretization scheme. And a cell Reynolds number of 2 also we saw was quite hard to achieve in practice. For a real simulation, the cell Reynolds number might be 100,000, could be very big actually. So this very, very bad idea to use just a central space scheme. So this very hard to avoid. So there, the first then, well, yeah, this is something actually also we should talk about a little bit. 3 topics that you should have in mind here. Conservativeness, meaning that your calculation of a flux over a phase in one of your volumes, you sort of calculate what goes through this wall, say during one time step of a quantity. Could be continuity equation, could be momentum, could be energy, could be whatever. But one way to calculate it is if you are standing inside this volume and then you calculate, okay, what will this cell push out? So you sort of look at it from this side only. Another way is to look at the next cell and ask, okay, how much comes in here? And if you don't get the same answer with those 2 different views, then you're in trouble. Then it's not conservative. Then the fluxes, of course, should be the same, regardless of the view from one cell to the next or the other way around. Of course, it should be the same. If it's not the same, you're in trouble. So, conservativeness. Boundedness will be then for your numerical scheme, that you have a solution that is bounded, and it's a pure numerical thing, and you have sort of the classical Scarborough criteria that to ensure equation system is bounded is, and then you have the criteria listed here. So it sort of has to be what is called diagonally dominant. To have a quick phrasing of it, you write your equation system on a matrix form, and then your coefficient matrix will typically be a very sparse matrix. Most of them will be zeros, but you will typically have some bonds like this. If it's a 1D case, you will have 3 bonds. If it's 2-dimensional, you will have 5. If it's 3-dimensional, you will have 7, and so on. But the diagonal values, the center point values, AP, should then be bigger than the sum of all the neighboring coefficients. Then you are certain that this will produce a bounded solution. And bounded meaning it shouldn't explode. So it's a pure numerical thing. And then finally, the last one, he calls it a transportiveness, sort of ensuring here that we have resolved the physics well enough. Remember the local, he calls it the Peclet number. I called it the local Reynolds number, which then was velocity, length scale, divided by viscosity. And this velocity, that's not the bulk velocity, this is the local velocity inside the cell with size delta x. So if the delta x is changing, you have to sort of here find, or actually check all the cell Reynolds numbers for all the cells and ensure that this one is smaller or equal to 2. That was sort of the criteria if you chose a central space scheme. If you choose an upwind scheme, you have different bounds. First order upwind, well, he was actually unconditionally stable no matter what you did. The cell Reynolds number could be anything. But then also you know the price. It was a very bad scheme. We have other that will again have other demands, more complex one. We will see them soon enough. So it's sort of a demand for spatial resolution. You need a certain amount of cells to describe the physics more or less correct. So yeah, conservativeness, boundedness, and this transportiveness. Fair enough. So central scheme is a problem if you don't have these criteria correct. First order upwind, well, you know already, and it's a terrible, awful. It's a first order accurate and should never ever be used, but it is unconditionally stable. So that was nice with it. So here the same example as with the previous graph that we had with the central scheme that went totally crazy. Now you will get a solution, but it's way off from the correct or exact analytical solution for this example. Way too much diffusion into the problem. Also, this example you have seen before. You send in a constant velocity field. The velocities are given. We know the velocities. They go in a 45-degree angle. And then our unknown function, phi, whatever that may be, it has a constant value here and then 0 at the bottom. And the correct solution then should be a very sharp jump across this diagonal line at 45 degrees if you don't have any viscosity into your problem. So we looked at this example and found out that for the central scheme, then you had the very funny problem that you ended up with a coefficient matrix where the diagonal just had zeros. And you have some other bonds. And the diagonal with zeros shouldn't be possible to solve. But for this example, yes, it was possible. You could sort of nest your solution if you start down here in the corner and spread your solution from the boundaries. It's still possible to find the solution here with finite difference, central scheme. But that's actually not a good point here. The point was using the first order upwind scheme here, and then we saw the solution smooth out this sharp jump, like you see here. And it really doesn't help if you try to increase the number of cells. I mean, 10 by 10 is very terrible, it smears out the sudden jump a lot. But even going to 100, you still have a smearing effect. So you could have gone to 10,000 by 10,000, you would still have this smearing effect. It really doesn't help. So the first order upwind is very diffusive. He adds viscosity to something that should not have viscosity at all. Not good. The hybrid scheme, that is sort of a mix between the central scheme and the first order upwind. So whenever you are in an area where the cell Reynolds number becomes bigger than 2, you jump to the first order upwind scheme. Else you use the central scheme. So the philosophy wasn't so stupid, but it's not the best scheme. So let's see if we have an example here. We have something. The hybrid. He doesn't really conclude with it. Say it's only as with the first order upwind. It's just a first order accurate scheme. So no, it's the hybrid scheme is actually not a good remedy. Going to higher order schemes, such as quick. Now this is something else. Quick, that's a quadratic upwind scheme, and that's second order accurate. And that one is actually not so stupid again. It's still an upwind scheme, yes, but at least it's more accurate than the first order upwind. It's not as stable, it's not unconditionally stable, but still better. You have other schemes as well. Power law, also not so bad, but still, well, only second order if you do it properly. So I won't go through all the details here with the different schemes because there are many, but at least give you the names of the most important. So the power law I don't think is much in use anymore. The quick scheme you will find, quadratic upwind. So that means when you are looking, say, at your center point P, and we had east and we had west, and then the question was, what should the value be here on this western border of your cell for any quantity? And typically then you are talking this U phi on the western border. What should it be? And then it's a question of the sign here. So now if this one is positive, information is traveling to the right, first order upwind, we just use the value to the left for these quantities to estimate what it is here. A central scheme, you can just take the average between these two. A quadratic upwind scheme, well, then you are going to need the other neighbor as well. You're going west-west. So you go an additional cell away to interpolate what should the value be here. This can, of course, be a little bit messy if you look at the boundary cells. So here you have a solid wall. If you think in terms of the solar code, for instance, then you had your first live cell here, and you have a pressure inside here, and we had the velocities here and so on. So now if you want to use a quadratic upwind scheme here, then, well, you are going to need some information what's happening inside the wall, and in worst case scenario you are actually going to need to know what is going on 2 cells inside the wall. Thank you very much. What's going on there? That makes it rather messy. So of course for boundary conditions you can't go 2 neighbors into the wall. That doesn't make sense. So there you have to do something special. So it can be a little bit messy with this taking next neighbor into account. But this quick scheme, it's second order accurate and quite popular. And yes, this is something that we can find in open form. And it is conservative. Maybe it doesn't look like it at the first glance. Sort of using this polynomial here. to evaluate what should the value be here, but it is actually consistent with calculating it from one cell or the other cell. So the fluxes will be conservative, as we call it. Quadratic upwind, very popular. We have that's an exact assessment. Yes, it's very good. And stability problems. It's not so stable as the first order upwind. So here you will also have demands for some spatial resolution for the cell reynolds number, but absolutely not so stupid. Here a problem again where we have removed the viscosity. So the correct solution is just a sudden jump, and the upwind, first order upwind scheme smears out, and there you see what the quick scheme does. He gives a little bit overshoot, and I think we did a demonstration of the advection equation, if you can recall. Then actually it was a transient problem. So we did it like this: du dx equal to 0, a pure finite difference advection equation. And then we looked at a case where we had an initial disturbance like this in space, and up here you had now the unknown u. And then we looked at how this initial signal, how he moved with the velocity a0. I mean, this is a pure advection equation, so he should only advect or move this signal undisturbed with a constant velocity. I mean, this is a linearized version of the advection equation, or the convective terms in the Navier-Stokes. So the correct solution will be this square block. It's just moved. But when we now tried with central differencing, it always blew up. It's unconditionally unstable. It's not possible to find a solution in general for this equation with finite difference central scheme. So we went to first order upwind, and we found this solution. He smears out the gradients, and if you continue, he will just smear it out, and everything will just disappear. So what you see now with this quick scheme, if we had used quick, okay, then we would have gotten a solution that would look something like this. So you get a little overshoot. Well, maybe even he may go down here. I'm not so... Yeah, I haven't tested it. I think maybe he will look something like this. But a little overshoot sort of on the shoulders here. So the boundedness is not perfect here. It's not completely bounded. Bounding means that you should have a solution that should lie between your biggest and the smallest value of all the other values that you have in the domain. So you shouldn't produce solutions with numbers bigger than any of the other values that you have in the domain. So a little bit overshoot. More advanced schemes, more modern schemes, something called TVD schemes, total variation diminishing. So these schemes, they are a little bit more complex, but higher order accuracy, and they will soften down such overshoots, yes, and they will ensure that the boundedness will occur at least in time, or in given enough iterations. We have other classes in numerics that will go into these schemes in more detail. The course with Professor Miller, numerical mass and heat transfer, covered these schemes quite nicely. So I won't go through them, but you should be aware of the names. Now these TVD schemes, they have sort of used this limiter function, Upc, which then it's sort of a function of this argument with this ratio r depending on your unknowns. Yeah, you can see for yourself here. Center point minus west, and then east minus center point. What's the function of this ratio? And you have a lot of different schemes then depending on where you are in this phi as a function of r scheme. But I won't go through the details here. We don't have time either, so. Let's see, you have, describing the different schemes here. What is more important for us is, there should be a list here somewhere. Yeah, you have to be within certain region here to obtain total variation and diminishing. So here you have sort of given this limiter function and the corresponding names of the different schemes. And here you will actually find several of these in OpenFOAM. Van Leer we have, Albana I don't think we have, Minmod we have, SuperB we have, Quick, and so on. So you will find several of these schemes available in OpenFOAM. So, and the effect, quite good for the advanced schemes, but they will never, none of them will be as stable as the first order upwind. So at the end of the day, let's see if it has an overview, you might use the following philosophy then. Didn't you have an overview here? No. Van Leer, Van Albana. No. I thought he had an overview in the end here. No. No. Never mind. You can think as follows. You want to have a solution, you want a steady state solution. You don't care about the time development now, just look at the steady state problem. And you want to solve your problem nicely, of course, and quick. Now we know that we have some quite advanced and good accuracy with these modern upwind upstream schemes, since the central difference scheme gives us a lot of problems. Now the central scheme will be more accurate actually than any of these if you could use it, but in practice no, you can't really use it. It's not stable enough. It's just going to explode. So we sort of have no option. We have to jump into one of these more advanced models. But many of them will be unstable, depending on the problem. So what should we do? Well, one solution would then be as follows. Start with the first order upwind scheme. It is terrible, it's awful, we know that, but it's unconditionally stable. So you obtain a solution. The solution will be bad, but at least you get a solution. Then you use that solution as an initial solution, initial value for any of these more advanced methods afterwards. That's what's been done for a lot of cases. So, and that's actually how we still can use this first order upwind scheme. Okay. Any questions from you?
Here, when you were saying stability, you you are not meaning time stability.
Exactly. We haven't mentioned time derivative yet. So the stability now, that will be safe to have your solution bounded, for instance, that it doesn't explode. So think of it as numerical stability, just for solving an algebraic equation system.
It depends on the initial guess?
It can depend on the initial state, yes. It doesn't have to, but it can. Remember, if you give him an impossible problem, like you want to describe some physics and you give him 2 cells to do it, that's not possible. He can't do it. So that you may risk finding a solution, but it can be very silly. More natural, he will explode in your face regardless what you do. You can try to give him a smooth initial solution that may be more or less stupid, but he can still explode in your face. Other questions? Then we take a break.